Welcome, I'm Simon and I will teach you quantum hardware design. In this video, we will take a look at FPGA PCB design. It's part 5 and it's one of the final parts of our series of designing full stack of quantum hardware computer. You can see kind of design the board of our control FPGA compute module. Here is FPGA, here is some memories, RAM memories. There is flash memory to store your data here, and there is kind of power circuitry. Let's move on to the next slide. The structure of this video is 30 minutes introduction to PCB layout, circuits, schematics, kind of principles and techniques and guides and tips and design guidelines and rules which you need to follow to design a good FPGA control board. So this is our theory part, and for design parts, I think it might actually be 30 minutes instead of 50 minutes. It will be quite short or just shorter than usual. Now, PCB layout design, this is what we're gonna discuss in the part. So it will be a really comprehensive PCB layout design, preparing files for manufacturing and talking about actual designing stuff and usage of the software to really design your FPGA and to create something valuable. Usage in different quantum computer types. So there are two main types which can use the spin qubit technology, or which can be used. It can either be used in a spin qubit technology or in superconducting technology, which is popular and leading technology for quantum computer types. So here is quantum computer architecture. It starts with control electronics, and this is really the R area of interest. And this is the like room temperature control stuff where we actually place our electronics. So this is very interesting. So the control electronics is what we care about, and when we go down, we can go to the cryo temperatures, and we can see um, the really cryo operation devices. So here are rules for high-speed PCB design. High-speed PCB design requires differential pairs, which is for the specific kind of connections. You can see the traces are very near to each other, and it is very beneficial for kind of clearing and getting rid of unwanted behavior. So this is really differential pairs. Then there is length tuning, which is great for kind of connections to memories and for buses and stuff like this. So length tuning, very important. Then there is controlled impedance. Controlled impedance is a requirement for RF circuits and mixed signal boards, and also the high-speed designs and stuff which requires connection, which can go up to the gigahertz range and requires a very precise tuning for memories. So controlled impedance is very important, that there won't be any reflections or unwanted behavior. Another kind of point is good layer stack planning. This is very important as well. Then there is proper component planning and placement. This is a requirement for good PCB design, and for good thermal kind of stuff and good connections. Then there's another thing which is impedance matched PCB traces. It also depends on the width of conductor, thickness of the substrate, type of the electrics, tripline or coplanar, and for differential pairs, it also depends on how close to each other are they placed, and really, mm, I mean, to the ground plane. Um, so choosing PCB substrate, different substrates for PCBs. FR4 is cheap and a low frequency. Mm, I mean, this is mainly used for digital designs. So FR4 is quite good for digital designs. Ceramic is expensive and can go to very high frequencies, and it's quite a requirement for high power and RF circuitry. So ceramic is very nice for high frequencies circuits. Then there is another option which is combination, which is mainly for kind of mixed signals boards, and this is FR4 and ceramic substrate. So there is simulation of mixed signal boards, and simulation of this is kind of, you can either use built-in feature, which is great for kind of the analog and lower frequency stuff and some thermal calculations. For RF stuff, if you use mixed signal boards, you should use AVR or Keysight import model. This is very good for early evaluating the S parameters and the kind of circuit simulation and scattering matrices. Then you might need to export the layout to FEM simulator and really evaluate its like properties in some FEM simulator. More comprehensive simulations are being done here, and then you can use any simple free tools, uh, which is for really kind of people who are starting out and just want to test mm, the capabilities of the software and evaluate the kind of properties and stuff, right? So this is our simulation. There is a high-speed PCB design breakdown. For higher RF PCBs, I mean, kind of meaning, I kind of mean even higher frequencies, high speed, digital design, FPGA boards. So this is our case. So there are some guidelines. Where bias should be as close to the IC, and they should be in some order. So you can take a look to the ball grid array to memory. So this is really our bias placement. So this is very nice. Components. Decoupling capacitors should be as close to the IC as possible, and the ground bias for these components should be as close to the components and the shortest track possible. Each layer uh, should be for each separate connections and type of routing. So you can see you have some high-speed connection to memories or to connectors. They're length tuned and they're differential pairs. So this is like one layer for high-speed digital design, and then you have a layer for power and ground planes and polygons and kind of stuff like this. So this is another layer, and then you might have casual layer just for any connections which are just unrouted or remaining, or uh, really uh, kind of not very important. Uh, you should have uniform and nice polygons for either high current tracks or some important ground planes and stuff like this. And they should be like low impedance connections. Nice clean layout, and should be stylish and well prepared. So I attached the picture of our 3D view of FPGA compute board. You can see it is in nice order, very well prepared, and in kind of nice setting. So this is really R. So this is RF PCB. In some cases, you might really use mixed signal boards with kind of RF PCB circuitry, and also um, digital circuitry attached to the board. So this is really for higher RF PCBs, so it remains same as in previous videos. Via stitching and shielding, etched RF connectors for lowest unwanted behavior and parasitics, edge plating, component closest to ICs, and traces uncovered. Um, Traces for DC matched and symmetric style. Also DC connectors, simple and lowest impedance as possible. So there are some RF PCB design rules for mixed signal boards, short traces, little meanders, and controlled impedance, of course. And this is basically it. So this is really our uh, layout even for RF amplifiers, for quantum chips, and for really our FPGA designs. So it remains same. You will start with concept, then do lumped elements. Uh, in some cases, you might actually not need to do really simulation of FPGAs before you design them. uh, you might actually skip the part of lumped elements and circuit simulation by actually just following some guidelines from a datasheet and for some application notes. So you might abandon the circuit simulation and go straight to layout, but it really depends on the kind of mm, how advanced your design is. Then you do layout, and once you have your layout, you need to do FEM simulation to ensure proper and reliable uh, operation, and also high performance and some certifications. And now you move to fabrication, and once the fabrication is done, you need to do some certification, and really you might be able to order it to someone. So this is our PCB design tool kind of selection guide. You might go with Altium Designer, which is paid and very strong, and it requires a lot of design knowledge and a lot of skills, which would take some time to learn and practice. So the designers usually need to be skilled and really well prepared to really know the software very well. So this is Ultimate Designer, but once they follow the tutorials and they really learn how to design stuff using a lot of different techniques and styles and follow the requirements and guidelines. They're very well prepared and they can use the Ultimate Designer. KiCad is very simple and free. It's usually not for uh, very advanced designs, but it's very quick and good for starters. If you really aim to be a professional, you should really start with Ultimate Designer. There are circuit simulation tools for mixed signal kind of layout boards, and if you also want to simulate the performance of high-speed circuits, you might actually use some RF studios and tools like eSight and AVR. There are some FEM simulation tools which you might need to really kind of ensure and verify the mechanical properties, electrical properties, and thermal properties. So this is for really uh, advanced designs in really high-end stage. With manufacturer PCBs, there are many options. It really depends on the quantity, quality, price, approach to customers, and your needs. So there are many options. It really depends on your needs. Uh, so there is process manufacturing PCBs, like process of manufacturing PCBs. It starts with really the manufacturing the PCB itself, the board. Once you have PCB manufactured, you can move to SMT assembly, where you put your components on the PCB and you just place them properly, and now you can move to reflow soldering, and this is your SMT board actually completed. If you have like two-sided board, it might be more complicated because it would be more costly and it would require more process, but more advanced kind of foundries can take care of this process very well. For a few additional through-hole technology components, you might um, really pay some extra fee, and this is like basically all you need to do. They just take care of this because they have some process where people either uh, like hand solder it and put it on, or they use some robots who take care of this process. Mm. So this is really process of manufacturing PCBs. Some things to notice when choosing a manufacturer. It should be quality of his products, his care and approach, speed, also price. Like the price should be as low possible, and yeah, this is what you actually need. Price and quality, lowest price, highest quality possible. Quantity, they should be able to supply you with required quantities. Reliability, so if you really uh, mm, if you really go to some manufacturer, you expect them to be uh, very reliable. Also, there is work ethic. Um, you should really expect your kind of fabricators to be approachable and online. preferably on weekends, and 24 hours, 7 days a week. So this is really comfortable for customers to really know the manufacturer really thinks about the customers and thinks about the kind of way they choose their uh, they just think about their customers and their needs. So there are some guidelines for choosing components. There are some things to keep in mind. Uh, it should be quality and origin of components, reliability, also lead times. You should expect your kind of supplier to have as short lead times as possible. Also the price should be as low as possible. And as the quantity goes up, the price goes down for the like one piece of components, if you know what I mean. There is documentation. The documentation should be very detailed, precise, intuitive, and also simple and understandable for your engineers. And there should be a very good life cycle. So when you design something, you can expect that the components will be available for as long time as possible. So you will get your components. Some tasks or some places where you can go. You can go to Altium Academy. You can follow Zach Peterson, Robert Ferenek, or Phil Salmony for guidelines and kind of tutorials how to design your FPGA board and compute module. So there are some handbooks and design materials for manufacturing. There is Ultium Design Manufacturing, the designer handbook for manufacturing, which is Sierra Circuits, uh, which is just from the manufacturing foundry or manufacturer. This is from the design software itself, and there's also some stuff and some things about controlled impedance. So if you have something important regarding professional stuff and career, please feel free to contact me either on LinkedIn or Gmail, whatever you like. So this is our schematic of an FPGA board, one of the schematic files, and it is DDR memory RAM routing. So here is a capacitor, and here is a connection to the voltage and ground. We can simply do this by choosing the symbols here and assigning the right names here. Now, once we have this done, we can go to wire, place a wire, and place the wire to the board, which can be chosen from here. We can choose the name for the port here, and once we have the name for the port, we can go and choose the net label. So this is our connection to the DDR memory. It's very simple. Now there are resistors, and you can see there is connection for the power plane and resistor, and there is wire and a net name, and the net name tells us where it connects. So you can see it's DDR3 A0, and it connects to this pin here. Once we have this done, we can add the power converter, which is very simple, and it is here in this part of the schematic. Um, so this is our decoupling. We need to add a power port here and a ground port here, and then add the capacitors in the middle. So this is the capacitors. It's very simple. Once we have our schematics done, just one more thing. For bigger FPGA boards, you will have multiple banks, right? Like shown here. So you need to split your banks because the FPGA has so many pins it wouldn't fit on one page. So it might be split into multiple kind of files and schematic pages. So it is a great idea to really split your design to multiple different files, and then just assign a port, because the ports now can be shared between different pages. You can add a new page here, add new page schematic, and once we have our schematic done, we can go and create new PCB. I already created one. So this is how our PCB looks like. First, we need to start with really defining our rectangle. So we'll choose rectangle and go to keep out layer, and we define the rectangle. So this is really our rectangle in the keep out layer, and let me really define it in keep out layer. So this is really our rectangle, and once we have this done, we can go to tools, or design board shape, and define board shape from selected objects, and you can see it defined a board shape from us. So this is how we define our board shape. Once we have this done, we can go to pad and play the pad. So this is really our pad, and the whole dimension is our choice. We can go with 6 millimeters, or 5 millimeters, or 4 millimeters. This is quite a standard choice for holes. So this is really our hole. This is how we place our holes. Then we need to really place the components, and we can do this by simply dragging the components at the right places, so it is in nice order, and it kind of fits the board perfectly, and it is easy to route. So the FPGA is typically in the middle. Your RAM memories are close to each other and symmetrical, so it can be routed very easily to FPGA. And now you have flash memory, so it can be routed very well. Now you have uh, kind of power converter, or power kind of power dedicated place where you have all your converters and supplying power for FPGA. And now if we turn the board on the other side, you can see connectors. Those are board connectors, which connect by simply placing the board uh, on the lower, like you will put your board on the kind of the other board, which is below, and it will connect by simply connecting these connectors together by placing the board uh, over. The capacitors are typically placed below the FPGA board, because the FPGA board needs heavy decoupling and needs a lot of capacitors. So this is really a lot of capacitors here, and we can assign some descriptions and names and designators. And once we have this done, we can place the small components like LEDs, transistors, and crystals, and some resistors for RAM memories for some load. So this is really how you place your components on your FPGA board. Typically on your top layer, you will connect the simple connections. Then you have other layers which you can either pour by ground or so this is how you connect really your connectors to FPGA, and this is your power layer where you really connect your power to FPGA by placing big polygon pours. So this is very beneficial. And now you have, I'm not sure which layer is really how you place your DDR memories. You just simply, so this is probably the best way to show how you route your connectors and signals. You can see that there are differential pairs which are close to each other, and they are named uh, P and N. It stands for positive edge and negative edge, and the signal is IO34 and IO34, and so it kind of signifies it is the same kind of differential pair. So this is really how you route your differential pairs. Now you can see the little meanders here. This is for length tuning, so each uh, kind of route is length tuned now, so it won't have any delays. So this is how you really connect your FPGA. Um, um, and now you can place your polygon pour to really connect ground plane very easily. So you can just route from FPGA ground connection very shortly via which goes to the layer below, and it connects to the ground plane directly, so it's shortest and fastest connection. It is lowest impedance one. So this is how you really route your FPGA. For routing, you can use either simple routing, which is just simple as connecting two places, or you can go for interactive differential routing, which you choose in case you have differential pairs, but you need to select the pins which are differential before, or you can go with interactive multi-routing, and this is great for connecting a lot of connectors like here you can just simply go for interactive multi-routing and connect multiple pins at once. So this is how you simply um, kind of create your FPGA. Once you have your FPGA done, you can go to fabrication outputs, uh, Gerber files, and you can click the Gerber files and generate the output, and now you select millimeters, file name, and it's all predefined, and you just click apply. It will create Gerber files for you. And now you need to create NCDRL files, which are for creating holes and vias. So this is really NCDRL file, which is millimeters, and this is as simple as that. And now you have assembly outputs, and you can really generate your pick and place files. It will create an Excel sheet for you, and once you have your Excel, you can put your I would say you have for each component you have designator, name, and a location of your component, and you can simply just assign it a proper name which stands for, or proper code which stands for kind of mm, mm, which stands for uh, mm, for the component. And for the code you can go simply here and pick any type of component you want. So let's go for some AMD Xilinx FPGA, and you can just click the component here and you will see the number here. So you just copy the number from here and paste it into your Excel sheet, and once you have this done, it will automatically tell the manufacturer which component needs to be placed at a certain location. So this is how you tell the manufacturer how to really place your components. And then you simply put your Gerber files, which tells the really dimensions and copper traces and pores and polygons. So this is really a PCB description, and you send it to manufacturer and it will create a PCB for you. And then you combine it with your bill of materials and pick and place files, and it will create a PCB and assembled board for you. So this is all for my series how to design quantum computer, and this is all for this video about designing FPGA board. Oh, and that's a wrap. One more thing, if you have something to say, please feel free to contact me either on Gmail or LinkedIn. Thank you.